Ladies and gentlemen, it is an honor to have the opportunity to give my presentation here. The title is A Heuristic Model of Partial Interdiction Median Problem for Multi-Sawing Supply Systems. Afterward, PIM-MS problem is called for short. My presentation will be given in 4 parts. The first part, Introduction, which deals with the background and topic. The second part relates to models for PIM-MS problems. The third part concerns experiments, and the last part gives the conclusions. First, introduction. Supply systems undertake the important responsibility of supplying essential goods and services. Because of potential disruptions, facilities in supply systems may become disabled, which has serious consequences on the whole society. So the question is how to identify critical facilities whose failures can result in the most damage on the whole supply systems. The interdiction median model introduced in 2004 can solve the problem. However, the model depends on the 3 assumptions, which are not appropriate concerning complex situations. First, incapacitated facility. The capacity of any facility is without upper bound. Second, complete interdiction. A facility loses all its capacity upon interdiction. Third, single sawing. Each demand must be served by its closest available facility. Accordingly, we present the partial interdiction median problem for multi-sawing supply systems and attempt to solve it. That's all for the introduction, and now we can go on to the second part of my presentation, models for PIM-MS problems. The problem falls into the form of leader-follower hierarchical decisions. The upper level problem is to assign offensive resources to maximize the post-attack minimal operation cost. The lower level problem is to re-establish supply-demand relationship to minimize the operation cost. Therefore, we formulate it as a bi-level model. The formulations from 1 to 3 express the upper level problem. The lower level formulations are from 4 to 8. Constraint 2 is the budget limit of interdiction. Constraint 5 ensures that each facility is not beyond its remaining capacity to supply demand nodes. Constraint 6 claims that requirements of each demand node must be satisfied, no matter which facilities supply it. However, solving bi-level model is an NP-hard problem. We can make use of heuristic information to simplify the solving. Consider the lower level reassignment problem. In order to minimize the operation cost, demand node intends to select closer facility to satisfy the demand. On the other hand, within the capacity, each facility prefers to select closer demand nodes to minimize the operation cost. Based on this, we develop two heuristic strategies. The heuristic model is illustrated on this slide. Constraints 11 and 12 express heuristic strategy 1 and 2 respectively. Now, let's move away from the second part and switch over to the third part, experiments. At first, we show the flow diagram of experiments at the step of initialization based on swing data set. Facility capacity is arranged according to the capacity formula, while epsilon is the adjustment factor of facility capacity. The 1,500 random instances are generated within the ranges of different parameters. Subsequently, the gaps between objective values of PIM, MS, and corresponding optimal lower ones are calculated by IBM commercial software, CPLEX. According to the gap values, we classify the results into 4 groups, and the results are illustrated in Figure 2 and Figure 3. The total results are displayed in Figure 2. We can see that 83% of the cases can be solved with the gap ranging from 0 to 2%. In Figure 3, we further analyze the worst cases whose gaps are more than 10%. We note that the smaller value of R2P, the more worst cases appear. Therefore, the heuristic model can solve effectively PIM, MS problem when the amount of offensive resources is not too small. So much for the methodology of the experiment. Now, I would like to shift to the last part of my presentation, conclusions. To sum up, we make contributions as follows. First, partial interdiction median problem for multi-selling supply systems is introduced. Second, the bilevel model is developed to express the leader-follower hierarchical decision problem. Third, the heuristic model is studied to effectively solve original bilevel model. Further researches should concentrate on the model's solutions as well as comparisons with other facility interdiction problems. We have done some successive researches and found some interesting conclusions. First, we investigate the influence of capacity on effectiveness and observe the relationship between adjustment factor in capacity formula and the gaps. We conclude that the capacity has a non-monotonic relationship with effectiveness. Second, we compare partial interdiction and complete interdiction for multi-selling supply systems. Consider the results of data in the table. All the results are non-negative. That is, the post-attack operation cost is larger under partial interdiction assumption than that under complete interdiction. Third, partial interdiction for multi-thawing supply systems and that for single-thawing supply systems are comparatively studied. From the figure on this slide, we find that the vertical locations of the points representing results of single thawing are diverse relative to those of multi-thawing. Therefore, the conclusion is that offensive resources tend to centralize on certain facilities in multi-thawing supply systems, while dispersed to different facilities in single thawing supply systems. Okay, that's all. Thank you for your attention.